I want to make it clear, I'm representing a team of scientists that call ourselves the Right Climate Stuff Research Team. We're more than 25 retired scientists and engineers from the Johnson Space Center in Houston. Tom, who lives in Maine, is a member. Bob Bowman here is from Maryland. We have others from around the country who have joined with us. And we also have a few people from the Houston community who are not NASA former employees, but they are very highly credentialed research people from Shell Research and Dow Chemical that were studying this climate thing long before we NASA guys got interested. So I want to make it clear that this is a team effort, and I just happen to be the spokesman today. I want to talk a little bit about how the international climate community talks about how sensitive our climate is to CO2 and other greenhouse gases. The holy grail of climate science is trying to define something they call equilibrium climate sensitivity. And it's loosely defined as the global average temperature rise that will eventually result from doubling CO2 level in the atmosphere. If you read the IPCC reports, it's pretty loosely defined that way. And their more recent AR4 and AR5 reports are incomplete and misleading. The double CO2 level in the climate model solutions is artificially held constant. It's a step function forcing. But in actuality, the ecosystem of the Earth removes half of the CO2 emissions we put into the atmosphere every year, like clockwork. But in an equilibrium climate sensitivity solution, they're arbitrarily holding it constant, which is unrealistic. The other thing they don't tell you is that it takes more than 1,000 years for the climate to equilibrate to this artificial forcing and reach the final equilibrium sensitivity number. Our CO2 regulations are based on what's going to happen in the next 100 to 200 years. So equilibrium climate sensitivity is unrealistic, has nothing to do with our climate for the next 300 years. Yet that's what the EPA is using to regulate CO2 emissions. Things have really gotten out of kilter here. The other metric that climate science uses is called transient climate response, and that's defined as the global warming that would result from increasing atmospheric CO2 levels at a rate of 1% per year until the double CO2 level is reached. This also is very artificial, and it can only be calculated with a climate model. But it's more like the slow rate at which CO2 is rising in our atmosphere. Even now, at a fairly high rate of CO2 emissions, our CO2 levels are climbing only at about half this rate. So even that transient climate response metric is not realistic. So typical of climate science over-reliance on unvalidated models and not enough on data is that neither of the two metrics the IPCC uses, ECS and TCR, neither metric can be verified with physical data. You can't catch them. You can't question them. You have to have a very complex climate model to run and get these numbers. To me, they're totally meaningless. If you can't verify your crucial metric with data, what good is it? So I'm pretty, after looking at this for a couple years, I think I'm going to quit calling them climate scientists until they get a metric that can be verified with physical data. Because scientists look at data, not just models. So I'm going to talk about the difference in these two dynamic solutions that they get with climate models. I'm sorry. Forgot. I'm going to use this very simple spring mass damper system that most of us have a feel for the dynamics of. And I always like to take a complex dynamic model and have a simple model to think about it with. So in the ECS forcing function at the top, instantly you double CO2 in the atmosphere and you hold it constant forever. Artificially hold it constant. Well, think about what kind of force that is on this dynamic system. It means you're starting with the whole system stable and still with a constant wind force on it, and instantly you double that force. You can see what that spring mass system's going to do. With a light damper, it's going to start oscillating. And eventually, due to damping, it'll damp out and reach a new level. And that's analogous to what that equilibrium climate sensitivity would be. Now, talking to climate scientists, I guess I'll call them scientists today, the damper in their models is fairly large, so it kind of just gradually approaches that doubled ECS value. But let's look at the transient climate response, which is the lower forcing function. Just gradually change that. You can imagine what happens to this dynamic system if you start with it at rest and then gradually increase the force. It's just like taking your finger and gradually pushing it up. It's not going to oscillate. It's going to be in equilibrium all the time. And the mass is just going to gradually rise, which is analogous to a rising temperature. So if you gradually increase the force, this mass is just going to gradually move upwards without oscillating. And that's the way our climate is actually behaving with respect to any CO2 warming that's occurring. So our solution of this dynamic system, in which we're going to use temperature as a measure, the solution needs to look a lot like the forcing function. In fact, this really isn't a dynamics problem, it's a statics problem, and you don't need a big complicated climate model to find out how sensitive you are to CO2. And I will point that out in this presentation.
Are you okay?
I'm sorry, I'm looking at the wrong screen. So what we did to get a verifiable climate, we defined a new climate sensitivity metric that we call transient climate sensitivity. It's kind of like the transient climate response, but we're saying transient climate sensitivity is the rise in global average surface temperature due to the actual gradual rise of greenhouse gases in our atmosphere in the year that the radiative force of the greenhouse gas is doubled with respect to pre-industrial levels. You can verify that because we have data on temperature, we have data on greenhouse gases, and we can find out, and we'll show you how we did it. We can define this TCS value for CO2 only, all greenhouse gases, or any specific greenhouse gas. If you're going to regulate CO2, and you're going to talk about how much damage you're going to avoid by regulating CO2, you need to separate the effect of CO2 from all the other greenhouse gases, because all the other greenhouse gases contribute about 60% of what CO2 does. And when the IPCC talks about ECS, they're usually talking about the effect of all greenhouse gases. So we need a CO2 only transient climate sensitivity value if we're going to talk about the benefits of regulating CO2 emissions. I want to put the double CO2 in perspective. This is where we started from, this very low level. That was CO2 in the atmosphere. This dashed green line is CO2 level you need in the atmosphere just to get plants to grow. If you don't have that much CO2 in the atmosphere, plants start dying. And we're talking about starting at this very low level, near the critical limit for plant growth, and doubling it. And right now we're about 40% along the way to doubling it from pre-industrial conditions. This is what we allow on the space station for astronauts to breathe, 5,000 parts per minute. I think Walt said on Apollo, we didn't know as much about CO2. His alarm went off at 4,000 parts per million. And this is what you allow on submarines, 8,000 parts per million, and those guys are under the water for 6 months at a time. So in terms of toxicity to humans or any other animals, we're way down here. We're never going to get CO2 levels this high in the atmosphere. You could burn all the fossil fuels on Earth, and you're probably not going to get over 1,000 parts per million. So I want to put this doubling CO2 in perspective. This is the actual rise of CO2 in the atmosphere on a different scale. This comes from ice cores in the Antarctic. The blue part is what's been measured since 1979. And this is our projection for what's going to happen as fossil fuels become scarce. They're going to become more costly. We're going to have to go to alternate fuels. We predict, based on the economic analysis, that we're going to peak out at about 600 parts per million sometime in the next century. I'm going to have to get going here. I'm going to skip over the word charts and just from basic quantum mechanics considerations, if you double CO2 in the atmosphere, we're going to slow down the radiation to outer space, and we will get an equation like this that says the radiative force change in any year is equal to 3.7 watts per meter squared times the logarithm of the CO2 in any year divided by the CO2 level in 1850 divided by 2. So when you get the double value, when this is double this value, this is 1, and we get 3.7 watts per meter radiative force. We're going to force the atmosphere with that. And that gets us to the temperature change should be given by this equation, just based on a linear change in temperature with radiative forcing. So we did a study where we looked at forcing the atmosphere with CO2 or any greenhouse gas, and we also looked at perhaps there were natural phenomena going on. This is the actual temperature data. The Hadcrut-4 data set, and you can see it has a general upward trend, but it's got some oscillatory aspects to it, you know, going up and down, that we said, hey, that's not that slow rise in CO2, that's something else going on. And we've, in fact, found a 62-year cycle in the data. This is a 1,000-year cycle that was going on before we started rising CO2 in the atmosphere. So this is how we model that Hadcrut-4 data, and we fit it with the CO2 forcing function. The wiggly line here is a 62-year cycle we found in the data, and the dashed red line is the maximum effect that CO2 could be having. Notice it hits the peaks of this red line. The green line, yeah, okay. So this is the way we